The broadcast is now starting. All attendees are in listen-only mode.
Hi, everyone. Welcome to today's past performance virtual group meeting. And welcome to 2020. Glad to have you join us today. I'm going to go through just a few quick items and then we'll get it over to our speaker. If I can select the right buttons. All right. Excuse me. My name is Leslie Weed. I am the president of the virtual performance group. If you are interested in volunteering and being part of the group, let me know. Our Twitter, our hashtag, our website, discussion list, email. Feel free to email us if you have specific topics you would like us to track speakers down for. We know a bunch of people and we know a lot of experts out there, so more than happy to track down those topics. All right. If you are new to GoToWebinar, we do suggest you maximize your screen and we will be taking questions. There is a questions pane in that little dialog box you have. So feel free to put questions in there. And just a reminder, we are recording this and we will have this up on the YouTube site, hopefully by end of tomorrow. All right. So big thanks to SolarWinds. They are our sponsor this year. And they have lots of great products. So if you are looking for a good monitoring tool, either for platform or network, check out their items. They've got a lot of good stuff. They just opened registration for Past Summit 2020. Of course, that's going to be in Texas this year, not in Seattle. So if you've never been to a summit before, you might want to put that on your bucket list because it's fantastic. All right. Past Marathon, Spanish edition. I think I'm going to have to listen to this. I won't understand the lick of it, but I think I have to listen to it anyways. I think this will be fantastic. Few upcoming virtual group webinars. Hopefully you guys get on the past.org website and stay up to date on what's going on. They have this full list up to date, so you can always check to see what's going on. Lots of different virtual groups out there. Upcoming SQL Saturdays. This got cut off a little bit, but Nashville, Cleveland, Austin, St. Louis, South Florida, Tampa, Rochester, and then of course we got some around the world too. And if you didn't know, Past.org does have a career center. You can go check this out at Past.org Careers. And you can contact directly with Past.org through Past TV. And if you don't have a membership, you should have a membership. All right, so we're going to kick it over to our speaker, Anthony Nocentino. Did I say that right? I probably didn't say that right.
Nope, you're good.
Okay. I was going to ask you and I forgot. All right, topic today is monitoring Linux performance for the SQL Server admin. So welcome, Anthony. Let me make you presenter here real fast and we'll get you switched over.
Cool, thank you.
If I can find the magic buttons. Okay, you should now be presenter.
Cool, thank you so much. All right, so let's get started. This is monitoring Linux performance for the SQL administrator. And I am Anthony Nocentino, and I'm a consultant and trainer and founder of Nocentino Systems, where I specialize in system architecture and performance. So this being the performance virtual group, I think it's a good topic for today. I have an undergraduate degree and a master's degree in computer science. We'll talk a little bit about those things actually throughout today's session, specifically operating systems, and I'm a data platform MVP. There's my contact info. It'll show up again later at the end of the deck, but please feel free to email me if you have any questions. Follow me on Twitter, and I blog relatively frequently, so go ahead and check out the blog there. Lots of topics around Linux, performance, containers, and Kubernetes, and I'm also a Pluralsight author, where I do have a course on SQL Server on Linux and also a deep dive into Linux performance, and I'll reference those at the end of today's session. And so for today's session, we're going to cover a lot in hopefully an hour, maybe a little bit more than an hour. That's your warning. But we're going to go through lots of things. We're going to talk about the Linux system architecture, like what Linux looks like inside from an operating system standpoint. And then we need to look at how SQL Server runs on Linux and how it's implemented in a unique way, and the interactions between SQL Server, the process running on Linux, and the underlying operating system. And so we'll focus a lot on that. And then what we'll do, once we kind of know the lay of the land from an OS standpoint and the application that we need to support, which is SQL Server, we're going to focus on the system components inside of an operating system. We're going to look at three big things. We're going to look at CPU, memory, and disk, and then the core operating systems abstractions, processes, pages, and then file systems. And what we're going to do is kind of look at how they work from an operating system standpoint in the theory, but then we're going to talk about what's good and what's bad and what you need to look for inside of Linux and where you need to look for it, right? And so the tooling that you need to do to probe each one of these main system resources, CPU, memory, and disk. And then once we're done with that, we'll kind of zoom out and talk about monitoring tools in general, like how we can start answering that larger question of benchmarking and baselining. So we're going to set some parameters. So I want to talk about the things that we're going to cover today. We're going to talk about the Linux operating system and how it works. And we're going to focus a lot on how to view perf data, like where we're going to look, and also what's good and what's bad, right? So when do I know this is something that I need to pay more attention to when it comes to what CPU, disk, or memory, what's being consumed, how it's being consumed, and what's a bad value, right? Or when the system is about to tip over and things go south. Now, what we're not going to cover is things like SQL Server internals and performance troubleshooting. You know, we're not going to do like query plans. We're not going to focus on things like latching and locking. That stuff is all the same effectively when it comes to how SQL Server works. And if there's any questions around that, please feel free to hit me up when talking about like what's going on inside of SQL Server and how it really is just SQL Server inside of Linux. So from an operating system standpoint, let's talk about the Linux architecture. An operating system really has one job. What that is to control access to the physical resources in your computer. So the hardware, right? There's things like CPU, memory, and disk. And the core of an operating system is this thing called the kernel, which has the responsibility of resource management, basically allocating the resources, and then also controlling access to those resources, so concurrency and things like that. Basically, what's on the processor at a point in time, who's in a particular memory location at a point in time, and which block is occupied by which file at a particular point in time. That's the responsibility of the kernel to make those translations and allocations. Now, when we're talking about that, things like processes, pages, and file systems, those are the core OS abstractions. So when I look at a process list, that's going to be what is going to be allocated to the CPU or what needs to be run on the CPU. If I'm looking at memory and how much memory is being consumed, well, we're going to look at that in terms of pages. And similarly with file systems and blocks. And we'll talk more about those abstractions as we go through each of the core major system components. Now, the shell inside of an operating system is where our programs are going to execute, right? It's basically our interface to the kernel. And so when we need to execute a program, well, the program's going to get up and running, and it's going to access the kernel via what's called the system call interface. So anytime a program needs to create a new process or allocate a piece of memory or a page, it's going to do that via the system call interface. Now, at the top of the Linux architecture is us, right? We're users, we interact with the shell, and we have one goal, and that's to cause problems, right? But this is basically the operating system stack. We have users who access programs that are running in a shell. The programs access the resources inside the system via the kernel, and the kernel is controlling access to the actual hardware. And now there's two terms I want to throw at you here is kernel space and user space. And so when a program is up and running and doing the things that it needs to do in terms of calculations or moving the data around that it has in memory already, that means that program is going to be executing in user space or driving that program state forward to accomplish the goals of whatever it is that our program does. Now, if a program needs to access a resource, perhaps it needs to perform I/O or it's waiting for a piece of memory, then you're going to transition into kernel space and you're not moving the program state forward. So the idea is we want to stay in user space as much as possible, but of course we're going to transition to kernel space periodically when we need to access resources. And we're going to focus on that when we get into looking at how things get allocated inside the CPU and also throughout the memory and disk portions of today's talk. So that's Linux, right? Now let's talk about SQL Server on Linux. So in 2017, and specifically in SQL Server 2017, the product team came out with this magic to be able to run SQL Server on Linux. And it wasn't a direct port. They literally did not rewrite, I shouldn't say that, but the core part of the database engine wasn't rewritten. In fact, in the center of SQL Server on Linux, it's still a Win32 binary executing inside of this thing called SQL Pal or SQL Platform Abstraction Layer. Now that SQL PAL is effectively a wrapper. I don't want to use the word container because that means something totally different, but it's effectively a place in which SQL Server, the Win32 binary, can execute thinking that it's running inside of Windows. So if you look at the core of that image there, we see Windows calls 1200 plus. And so as SQL Server needs to interact with our operating system, perhaps execute system calls, it's going to do that against SQL PAL. And then SQL PAL has the responsibility of translating that to Linux system calls. And so that whole time, SQL Server thinks it's running inside of a Win32 process space and it's executing Windows system calls. But it's the responsibility of the SQL PAL to translate those into Linux system calls. And you can see it kind of distills it down. In the middle there, you see ABI calls, 50. It distills it down to just 50 core interactions with the underlying base OS, right? When it needs to interact with the hardware or execute system calls. So when are we going to do that? When we need to access the resources of the real system. So again, CPU, disk, memory, network IO are going to be those reasons when that process needs to reach out into the base OS. And so let's start our journey kind of deep diving into how Linux works and monitoring in terms of CPU and the primary operating system abstraction, which is a process. And so what is a process? A process is an executing program, right? It's the program code, it's the memory and any resources associated with that process that are up and running. So things like file handles, network handles are all going to be part of that process address space. Now, processes also could have threads or lightweight processes, which have shared access to those resources. So I can have an individual process that has many, many, many threads, and they're all sharing the same memory space, same file handles, and collection of resources, so they can interact with them in a concurrent way. And so this is how we can add concurrency to our program's execution. Now, another part of what's important from a process standpoint is this concept of a process tree. And so inside of Linux, we're always going to have a parent and child relationship. And so when we look at SQL Server, when it's up and running in a little bit, when we start getting into the demonstrations, we'll see there's a parent process, a child process, and then many, many, many threads hanging off of that child process. If you kill a parent process, it will kill off all the child processes associated with that. And so we need to take that into account when we're managing the processes in our environment. Now, another big thing that we need to focus on when it comes to terms of what processes do and how they access the actual CPU in the system is scheduling. And in Linux, the unit of scheduling is the thread. And so each and every process will have at least one thread, and that thread is the thing that will get scheduled onto the CPU or the execution context of the thing that actually has to do work. The scheduler, much like in Windows, inside of Linux is preemptive and is based on a dynamic priority list. And so literally there's a bucket of, or I shouldn't say a bucket, it's like two metaphors. There's a collection of queues inside of the scheduler that are going to be built on of a dynamic priority list. And so as processes need to get onto the CPU, they'll get placed into one of those priority lists based on niceness, which is a numeric value associated with a process. And by default, all processes will have the same niceness, which is a default of 0, and land into a queue. But we can influence who's more important in getting access to the CPU by adjusting the niceness of a process. And so let's talk about process states now. And so when I have a process inside of Linux, I could be up and running. And then from that state, I can transition into another state, which is sleeping. And the reason why I would transition to sleeping, there's a couple of reasons. One is I've exhausted my quantum. I've gone beyond the amount of time that the operating system will allow me to be on the CPU, and I'll transition to a sleeping state. Another reason why I could transition to sleeping is I need to perform I/O. And so if I need to go reach out to a piece of disk or reach out to disk or reach out to the network, then I'm going to transition into a sleeping state that I/O will be conducted. And then once that happens, I'll move into the runnable state once my I/O has been complete. If I did get exhausted from a quantum standpoint, then I'll transition through sleeping and slide right into the runnable state. Now, this runnable state is when the scheduler has to make a decision based on those queues that we talked about on who gets selected and placed onto the processor next. And that process will then go back to the running state. So we can go back to doing the actual work to drive our program state forward. Now, from there, we can go to stopped and also my favorite state, which is zombie. And so stopped is going to be when our program is terminated execution. And zombie is when there's generally a pretty bad unhandled fault inside of our program. And for whatever reason, we've either crashed or become in an unhealthy state, and the operating system will then take that process, unlink it from its parent and link it to PID1 inside of the system, and that process will basically live forever until we reboot the system. And so that's why it's called zombie. Now that we kind of have the core lay of the land when it comes to how CPUs allocate processes and a rough understanding of how scheduling works and process states, let's talk about when we're looking at CPU inside of Linux, like what do we want to look for? Like what are the things that are interesting to us? And one of the core metrics that for eons people have been measuring CPU by is percentage, right? I'm like, percentage of what? Like what is the percentage of a processor being consumed? There's like a 4-core system with 3.5 gig processors. How do you compare that to another processor that's maybe 2 or 3 generations newer with the same clock rate? Like what does percentage actually mean? And so when I'm building high throughput, high performance systems, I don't focus on percentage, right? Because, well, if a processor is being consumed, that's cool, right? I want it to be consumed because that means it's doing work. Linux gives us another value that I think is much more critical to the throughput of a process getting work done inside of the operating system. That's load average. Load average effectively is the length of the run queue, which is the dynamic priority queues that we talked about when a process goes into the runnable state. If I have not a lot of processes in the runnable state, that means I'm getting high throughput and my processes are getting onto the CPU and doing their work. If those queues start to build up, well, then that's going to be latency in my application because that application can't get on the CPU to do the work that it needs to do, right? And that's when I start, when I want to start paying attention, when I start seeing queuing inside of the load average for a system, is that being the core metric. Now, in addition to queue length, that also takes into account IO weights. And so when we go, because that's one of the reasons why we would transition from running to sleeping is both IO and exhausting our quantum. So kind of like I alluded to a second ago, is high CPU is really not that bad of a thing, right? That just means we're consuming the CPU. If we start seeing queuing, then that's bad news. And so, but spikes in general aren't bad, right? That just means we're doing work. And so it depends on, I guess, the SLAs of our platform, right? If we're having a high throughput system that's OLTP, well, then we want to keep these things down. But if we're doing data warehousing or removing large chunks of data between systems, well, then of course we're going to see some level of sustained utilization and perhaps queuing. So it really depends on your workload. We also want to keep an eye out for long waits. Again, if we're looking for a high throughput system, are we constantly waiting on IO? And if that's the case, then we need to go and focus on that resource. And we'll talk a little bit more about IO and consumption when we get into disks towards the end of today's session. Now that we know what processes are and kind of what we need to look for, what are the tools that we can use to ask Linux to tell us these answers, right? To tell us what it's thinking about what's going on. And the core thing that you see on most Linux systems is kind of the go-to. It's basically Task Manager for Linux is top and HTOP. Top is available pretty much in every Linux distribution, and HTOP is a tool that you'll have to install to get access to that program, but it's kind of, for me, my go-to when it comes to figuring out what's going on from a resource standpoint in my system, and we'll use this in our upcoming demos. Dstat's another fantastic utility to answer the question, what's going on my system? It can give you things like user mode, kernel mode. It'll also give you CPU consumption. It'll give you memory utilization, swapping. It's kind of the monitoring Swiss Army knife. Now, PIDstat's a program that we're going to use today that allows us to dive deeper into what's going on inside of a process. And we're going to use that in our upcoming demos to kind of carve out what's really going on inside of our workload. And one of the core things inside of Linux when it comes to monitoring our system is this thing called procfs. Now, in Linux, there's a philosophy of everything as a file. So even a running process on a system is exposed to you as a file inside of a file system. And so we're going to look inside this thing called procfs, which is literally in a directory called /proc. And that's where we're going to surface up some really deep dive performance data. And so we're going to go dive through there and look at some pretty cool stuff. And so let's get into a demo and look at these things. We're going to look at processes and threads and execution. We're going to look at load average, right, under CPU saturation. And we're also going to kind of spelunk around inside of procfs. And so let's go and switch screens here into my demo box. And what I have here is on my MacBook Pro, I'm running a VM that is running CentOS 8 with 4 CPUs and 12 gigs of RAM allocated. I've just booted the system up, so cold caches across the board. And I have SQL Server on Linux installed, 2019 CU1. I have max memory set on that instance at 8 gigs, so 12 gigs total in the VM, but I'm limiting SQL Server to accessing an upper boundary of 8 gigs of RAM. I installed HTOP, and we have a connection here at the bottom to that server, which is my server name SQL1.lab. And I also have here the tools that I've installed. So if you want to pick up these demos, this should be able to get you to where you need to be when it comes to being able to reproduce these demos. I also have available in the download scripts a setup that builds a database and generates the data that we're going to be working with today. So let's get cooking. I'm going to go ahead and throw an environment variable in there for password, since I want to be able to use that over and over again. And the first tool that we're going to look at is HTOP. And like I said, it's kind of my go-to for when it comes to monitoring what's going on inside of my system. And you get a lot of information when you run HTOP and exposing what's going on the system. So let's kind of walk through all this together. So here we can see 4 charts or 4 graphs, one for each core that's available in the system. So there we see the utilization of those in terms of percent. We see the memory that's allocated. So we see I'm consuming just over a gig of my 11.5 gigs inside of the system. And right now I have no data inside of my swap file of a 7.89 gigabyte swap file. I have 31 processes up and running. So here we see that in tasks right here, and 181 threads. So these are actual allocated processes. And there we can see the ones that are actually on the CPU. We see 1 running. Now this is load average, right? This is the thing that I look at most when I'm looking at the performance of a system. And right now we see 0. So literally the length of the run queue to get access to the CPU on average is 0, because, well, literally nothing's running because my system's only been up for about an hour and I haven't gotten any workload going. Now you see 3 values here. This is the 1 minute, 15 minute, 1 minute, 5 minute, and 15 minute averages. So we can figure out what's going on right now, what's going on over the 5 minute average, and what's happened over the last 15 minutes. So we can kind of get a better feel for, is this a spiky workload? Like, are we really busy just right now? Or have we been busy over the last sustained 15-minute averages, right? And that's going to give us an indication of what's going on in our system. So at the bottom here now, I have a process listing. So here we can see the process ID. So there's PID1. If we go down a little bit further, we can see at 15, go down the bottom here, there are 1510, that SQL Server is up and running, and it's running as a user MS SQL. We can see its dynamic priority, so number 20, and its niceness is 0, so that's the default value. We can see the amount of virtual memory assigned to the process. We'll talk in more detail about that in the memory section. And also res, or resident set size. This is the actual amount of physical memory being consumed by this process. Let's go ahead and jump over to state. So here we can see all of these processes are sleeping. They're not actually on the CPU doing any work. And we can see the percent CPU consumption across all of the processes, and also the memory and the amount of time. On the right, we also see the actual binary that's up and running. So let me bring a couple more things into view, and you can kind of see that parent-child relationship of the processes and the threads. So process 1510 being the parent. Inside of the architecture of SQL Server on Linux, we have this thing, it's the watchdog process, which has the responsibility of starting up or forking a second process that is also a clone of the original process that is another SQL Server independent process. Now this process spins up a collection of threads that you can see are hanging off of process 2204. These all share the same memory space. And so there we see memory 8.1. And so that's the percentage allocated to this particular process. And that's the reason why it's the same, because it's a shared resource across all the processes that are executing, or all the threads that are executing inside of that 2204 process. Now 1510 has an independent memory space because it's an independent process. And so there we see its memory allocation is much smaller. So with that, let's go ahead and kick off a workload. And so I have a shell script here that's going to kick off checkDB. Oops, what's going on there? That's going to kick off checkDB running in a hard loop. So basically, I'm just running checkDB over and over and over again inside the system. And so the very first thing I want to call out, you see a lot of red CPU right here in the utilization. And so what that is kernel mode work, right? And so in this case, I had just booted up the system and I have cold caches. And so right now we're performing a lot of disk IO, right? To read that stuff in off of disk into memory to build the buffer pool. The second thing I want to point out is the growing memory. So as you watch, you'll see that this value for the memory allocations is going to grow. So 3.9, 4.0, 4.2, as we read that information in off disk. The green part of the process utilization is user mode execution. So that's stuff going on inside of the application. So in this case, our workload is checkDB. So that's the actual process that's occurring, is consuming this part of the CPU, but the red is kernel mode or IO, effectively what's going on there. And as we can see, our memory utilization is continuing to grow. We can also see our load average is upticking now too, right? So now we see that we have some load that's going on, and SQL Server is scheduling work onto the processor. And so we can see that four processes are basically up and running, and this will continue to grow until we hit a saturation point. So this value will plateau at around 4 at some point in time in the future if I continue to run this workload. But we know we're running hard right now, but we know a few minutes ago we weren't running so hard because you can see this value is a lot lower than the current load average, and much similarly at the 15-minute load average, that value continues to go down. If we go down into the bottom here and we look at the memory that's now allocated, we can see SQL Server is consuming just about 8 gigs of RAM. So that process 2204 is pretty much loaded up all the memory it needs to take to hit max server memory, which we stopped at 8 gigs. Cool. So let's break out of there and look at DStat real fast, another fantastic tool. And so DStat is going to give us kind of this incremental view rather than a graphical view of what's going on. So here we can see our utilization in user mode, system mode, when it comes to CPU consumption, and how much is idle. We can see disk IO and reads and writes, and we'll see this again later, but we can see I'm driving the IO really hard on the system to the tune of hundreds of megabytes. Now let's go ahead and jump out of here with the Control C and go ahead and kill that workload. And someone used the command kill to get rid of that checkDB process. Break out of there. And now we're going to shift gears and look at procfs. So if I look inside this directory, so literally if I do a directory listing on /proc, we're going to see a directory for each process that's up and running on our system. We also see a collection of files which have to do with the kind of the core configuration of our existing system. So on the left here, directories. On the right, these are going to be files that kind of represent the state of the system. So there we see CPU info and mem info. And so let's take a peek at CPU info so we kind of get a view of what's going on inside of there. So inside of CPU info, we're going to get kind of some deep dive information about our current processor configuration. And so that's just an example of the kind of data that's available inside of /proc. Now, pretty much all of the tooling that has to do with performance and emitting kind of what's going on from a perf data standpoint is going to come out of /proc. And so, for example, if I want to look at something like LSCPU, which is a program to give me the CPU information, well, that program's output looks awfully similar to the output that we just looked at by looking at that file directly. So just going to highlight the point that this is where all the tools get their information from and where we're going to go to when we need to get some deep dive information. And so let's go ahead and do that. Let's get the process ID of SQL Server, because remember, every process has a directory entry in /proc, and we can see we have two. We have 1510 and 2204. Remember, 1510 is the watchdog process. 2204 is the actual process that's driving our workload. And so I'm going to use some command line magic to switch into this directory and just say change into the proc directory and evaluate that expression to give me the process ID. And there you can see it changes me into the 2204 directory. And the reason why I do that is because you never know what the process ID is going to be when SQL Server starts up. And so that way you can go reproduce this on your own system and it'll dynamically change you into the current directory, or the correct directory, I should say. So let's look around inside of that. So here we're in /proc and we're inside a particular process. If I look around inside of here, we're going to see a lot of information about this specific process. And so we can see things like its memory allocations, or the current call stack, or the stat and status of the process. And so let's go ahead and kind of dive into a couple of these files in more detail. So if I want to get a feel for what's really going on, I can see the actual binary that's running by looking at the command line file, which is literally just a file on the file system. If I want to get into kind of the gory details of knowing what's going on inside of this process, I'm going to look at status. And inside of status, I'm going to see things like the name of the binary, the current state, its thread group ID, its parent process, or excuse me, its process ID, its parent process ID, and the UID and GID associated with the process. And so this is kind of some really deep dive stuff on what this particular process is doing. If we go down a little bit further, we're going to focus on this in the second part of today's session. We also get some gory details about the memory topology of this individual process. And so we're going to learn how we can look at this data to determine who's really doing things like swapping, which is potentially a bad operation when we're talking about the performance of our system. So that's the kind of information that's available to us inside of Procfs. So let's go ahead and jump back into our presentation, kind of review what we just covered. We looked pretty closely at processes and threads, and we saw how they could surface themselves inside of HTOP. And we also looked at load average, right, and how that shows us what's really going on from a workload standpoint on our system. And we also looked at what's going on inside of Procfs. So let's shift gears now and focus on memory and its primary abstraction inside of an operating system, a page. And so inside of Linux, let's kind of review or overview the memory layout and the architecture of how memory is consumed and allocated inside of Linux. So similar to most modern operating systems, you're going to have this concept of physical and virtual memory. And so physical memory being the actual amount of memory that's inside the system, right? So the actual physical chips. And so in today's case, you saw my virtual machine has 12 gigs of memory. So that's going to be the physical memory associated with that individual operating system. Now, processes don't access memory directly. They actually access virtual memory, and it's going to be an abstraction around the physical memory so that the operating system can control who is physically resident in a particular piece of memory at a particular point in time. And that's going to be important because then we can basically over allocate or multiplex the access to that hardware with this virtual memory concept. And so when we allocate memory inside of a process, we're going to access virtual memory, and it's the operating system's responsibility to map that back to the physical memory for us. Now, inside of Linux, we have this concept of NUMA awareness. And it's very similar to Windows in that we have free lists per nodes inside of an operating system. So your NUMA topology, when you're allocating memory, is NUMA aware. And so each one of those free lists are going to be a collection of pages that are available from the memory controller of that part of the operating, or that part of your hardware. Now, when we're looking at accounting data inside of the perfmon tools, when we're looking at the memory topology of our system, you're going to see this thing called an anonymous page. It doesn't mean that it doesn't know what's going on inside that page or it lacks any identity. What that means is that's just a page that's allocated to a user process. And so we'll see that come up in the data when we start looking more closely at the internals of what's going on inside of the memory allocations for a process. Now, this is where things get unique, demand paging. So if I am a process and I need to ask for memory, I told you earlier that when a process goes to allocate memory, it asks for a piece of memory and it gets access to virtual memory, and then it's the OS's responsibility to make sure that's backed by a real page. So if I'm a process and I start up and I ask for an amount of memory, well, I'm actually not going to get that memory until I write a piece of information to that virtual memory location. And that is going to then allocate the real page behind the scenes on the actual chips in my hardware. That's called a minor page fault. And those are going to execute in a very short amount of time, in a microsecond, nanosecond speeds, right? So very, very quickly. And now we have another scenario where we have to be concerned about a different type of page fault. And let's kind of focus on that. So if I'm a program and I'm up and running, there are scenarios where the operating system will basically say, you know what, I'm going to reclaim some of the physical memory that you have mapped into your virtual memory, and I'm going to take that information, or I'm going to take the data that you have in your virtual memory that's in my physical memory, and I'm going to write that out the disk. And that allows me to be able to reuse those pages for other processes in the operating system. And why would we do that? Well, there are two scenarios that we're going to see inside of Linux where our information could be swapped out, where basically the operating system is going to take a piece of memory away from me and potentially give it to somebody else. And those two reasons are time and pressure. So if I haven't used a piece of memory for a long period of time, well, Linux, the kswapd daemon will actually say, you know what, I'm going to take that, reclaim it, and put it back under the free list so someone else can use that. And another scenario is pressure, right? I'm running out of memory and have new processes that are starting up and need more memory, or maybe they're asking for more memory. And that's going to put pressure on the system. And so as those free lists get smaller, it's the responsibility of the operating system to kind of swap that information around so that those real pages can be assigned to newer processes. So time and pressure. All right, so now I have a process, it's up and running, parts of its memory space are written out to disk, and now I need to, from a program standpoint, need to go touch that piece of memory, that virtual memory. Well, when I do that, I need to get the actual data. So what's going to happen is, well, that's on disk now, and the kswapd, or the operating system, will read that information from disk, allocate a page, and put my data back into a real physical page. That's called a swap in. That's a major page fault. Now, I just described that I have to go retrieve that from disk, right? So that's a disk transaction that's occurring. So even in the absolute best high-speed SSDs that you're going to have, that's still going to be or millisecond to maybe microsecond latencies, and that's still an order of magnitude slower than memory, and that's a bad thing, right? That's where your system's going to tip over, and you're going to have really bad performance problems, and we're going to see that in our upcoming demos. Now, there's another cache that's available inside of Linux, outside of the core memory allocations for user processes, and that's the file system cache. So any leftover memory that's unallocated to user processes will be allocated to the file system cache. What that means is, as I'm traversing the directories and accessing data, the metadata and parts of the files that I'm accessing will be stored in the file system cache to increase the interactivity of me when I'm working with the system or my programs, right? I'll have metadata about disks information available inside this file system cache, so I increase the throughput or the performance when I'm interacting with the system. And that's cool. But there are scenarios where I need to take that extra memory that's allocated to the file system cache and tip that over and give it to user processes, right? And that's where this value called swappiness comes in. And the default value of swappiness is an integer value 10, which means at some point in time, it's going to tip over that cache and give it to user processes if I start running out of memory. And we'll look at that in a little bit when we start looking at the memory accounting information that's exposed inside the OS. So, all right, cool. So now that we know how memory works inside of Linux, what do we need to look for? Who's consuming the most space, right? That's kind of the biggest one, but in both terms of physical and virtual memory. We also need to understand external memory pressure on SQL Server. Inside of Windows, when there's external memory pressure on SQL Server, what SQL Server will do is it'll start dumping over its internal caches, so things like the plan cache and the buffer pool. It'll start evacuating those caches and releasing that memory back to the base OS to be allocated to other parts of the operating system. Well, in Linux, that boundary that is SQL kind of puts a unique scenario around that, and we're not going to get the exact same performance out of that process that we would on the Linux side of the house as we would on Windows. I'm going to show that to you when we get into the upcoming demos. We also need to look out for excessive swapping. The second you start swapping inside of an operating system, that's really when things kind of tip over and performance goes really, really, really south. And so you have to figure out who's consuming all of the memory and why, right? And maybe put some boundaries around that. Now, what happens if you don't have a swap file? So we see things like in Azure, when you deploy an Azure VM, that you might not have a swap file, or we'll see it in Kubernetes when you're running a container. Well, you literally don't have a swap file. And what's going to happen if we start swapping inside of a process due perhaps to external memory pressure? And I need to write memory out to virtual memory and out the disk. Well, what's going to happen is your process is going to die. And that can put you in a bad situation. You have this thing inside of Linux called the OOM killer, out of memory killer, that has the responsibility of killing a process if it is going to exceed the amount of memory that it needs to access and potentially start swapping. Now, in Kubernetes, we don't have a swap file in containers. And so if we need to swap, what's going to happen there? It's going to crash, right? Our program's going to die because we don't have that additional memory to access from a virtual memory standpoint during a swap operation. And how do you get around that? You have to engineer and design for that, right? You have to make sure that you're putting boundaries around how SQL Server works so you don't ever get in a scenario that you're swapped, and also make sure you don't have external memory pressure inside of your operating system to put pressure on SQL Server or any process really that's running inside of Kubernetes or in Linux with the OOM killer. That will then take out that process or that container. So what are the tools that we have to know what's going on from an accounting standpoint? Well, inside of /proc, we have meminfo, right? That's kind of deep dive into all the different types of memory that are available inside the OS. We have free, which is kind of the go-to tool to give us kind of the landscape of our memory consumption. Top and HTOP surfaces information, and also a tool called PS, which allows us to get a listing of the processes that are running on our system. Now, if I want to find out who's swapping, that's where I'm going to use these two tools, VMstat and PIDstat. So once I know I'm consuming some swap and I see it growing perhaps in HTOP, then I'm going to find out who, and I'm going to use VMstat and PIDstat to figure that out. And so let's go ahead and do that together. We're going to look at the memory layout of our system. We're going to find a memory hog or a high consumer of memory. We're going to kick off a process and cause some external memory pressure on SQL Server and see what happens. And we're going to look at what's going on when our processes start swapping and the influence that it has on the performance of our system. So let me get back into a particular directory. Go ahead and grab, where is it? That directory. Jump back down to our demo for number 2. And I'm going to go ahead and kick off this task here to warm up my buffer pool. And so this test DB1 with the table T1, is a table of exactly 16 gigs of data. And so I just read all of that data and output at that value. So I'm just basically ensuring that that's all loaded into the buffer pool. And so if I go and I look now at the memory accounting for the current state of the system, I can use free minus M. So free would give this to me in kilobytes, and M gives it to me in megabytes. We can see about 12 gigs, about 8.3 are used. I have about 2 gigs free, and I have a buffer cache, right, or the file system cache of about 1.3 gigs. Take these two values and add them together. So buff cache and free, that's what's available for user processes. Because remember, this can get tipped over and used for user processes in memory pressure scenarios. If I look at cat, if I get the output of proc meminfo with the cat program, and I'm gonna pipe that in that more so it doesn't fly off the screen, we can get kind of a really deep dive layout of the processes, the allocations of different types of memory in the system. So here we see the total, the current free, the current available, what's cached, what's active. Here we see active anonymous assigned to user processes. All right, let's go ahead and break out of there. Now, if we look at HTOP, again, so we know our cache is warm, and so there we see about 8 gigs is consumed. So the VM has 12, SQL Server is limited to using 8 because of max server memory, and I loaded a table that's got about 16 gigs of data in it. And so that's why we see that value plateauing at around 8. So it's gonna break out of here and jump into our SQL Server process again inside of procfs. So there we are in 2204. Here we can go and look more closely at this process. And so I have lots of different values here and the definitions of those for the memory accounting information that's available in the status file. And so we looked at this a second ago from a process standpoint, but let's look at it now from a memory standpoint. So we can see things like peak and current size. This is the peak virtual address space for this individual process. And I have 12 gigs in this system, and SQL Server thinks that it has approximately 18 gig virtual address space to allocate memory from. But we can see that it's backed by about 8 gigs of memory. So that's VM RSS, or resident set size, and this is the peak. So VM HWM is the peak amount of memory that was actually on the hardware in the system. And then we see RSS anonymous, so those are the user pages and also some file cached pages there. So let's do something not so nice to our system. Now what I'm gonna do is I'm gonna start a hard loop of reading from that T1 table. So that's what's inside that SQL file there. And if I go here and I look at HTOP, now we're gonna see my system's pretty pegged. And we're spending a lot of time in user mode, but also a lot of time in kernel mode. And the reason for that is that table is 16 gigs, max server memory is 8 gigs. And so we're constantly hitting the disk to bring new data pages in, right? So that's why we're driving a lot of IO and spending a lot of time in kernel time. So this could potentially be a bad scenario because PLE is gonna be super low. We're driving a bunch of disk IO, and this is a good way for us to see this in action. So let's go ahead and break out of here and do something even nastier. So with that workload up and running, where I'm constantly reading that 8 gig table over and over and over again, I'm gonna start another process that's gonna allocate 10 gigs of contiguous memory. Now remember, the whole operating system has 12 gigs, SQL Server is using 8, and I'm about to come along and say, hey, I need a process that has 10 gigs of contiguous memory. And so what that's gonna do is put pressure on the underlying operating system, because now the OS has to balance between SQL Server consuming what it wants and my process consuming what it wants in its 10 gig allocation. And so let's look at what happens in HTOP when I do this. So the first thing that we're going to see when that workload gets up and running is this. Well, first off, I don't think it is running. Let me see. Let me jump out. PS, memtest, HTOP. Yeah, it's growing, sorry. So we see we're going above 8 gigs, 9 gigs, 10 gigs. And so my memtest process is continuing to grow, and it's starting to hit the peak of the system. Now, both SQL Server wants 8 gigs, right? And it's driving that workload. And my memtest process wants 10 gigs. Well, that memory's got to come from somewhere, and that's going to come from swap. So we see swap growing now. So we see 3.4 gigs, 3.7 gigs. And so what's happening now is both of these processes are thrashing, right? SQL Server is getting swapped out, it's coming back into memory. My process is getting swapped out, it's coming back into memory. And if we look more closely at the individual processes, we can kind of get a good story of what's going on. So SQL Server was consuming 8 gigs of memory when we had just SQL Server up and running. But now my memtest process wants memory. And so what we can see is the resident set size, or the actual amount of memory that's in, or the actual amount of this process address space that's in physical memory is reducing, right? From 8 gigs to 3 gigs and so on. If we go down further and we look for my memtest process in the process list here, we're going to find its memory allocation. So let's look at that. Scroll a little faster. Let's go up in the list. Where is that? There it is. So memtest is consuming 10 gigs, and it's got 8 gigs that are in memory at this point in time. So 10 gigs being the whole virtual address space, and that 8,360 is their 8,400 is what's in physical memory. And so SQL Server and my memory pressure program are kind of trying to balance each other out, and it's a responsibility of the operating system to swap those in and out. So let's look at who's swapping. So we saw from HTOP that our swap was growing, and we can see from VMstat, we can see that we're swapping still pretty aggressively, swapping in swapping in pages from disk, right? And there we see a swap out. Now, if I want to find out who's swapping, that's where PIDstat comes in. If I do a PIDstat minus R, then it's going to be a sudo PIDstat minus R. I'm going to get the individual processes that are getting swapped. And so here we can see inside of this output, this is refreshing every 1 second. So I'm going to let it run for a little bit and then break out. If I scroll up, we can see what's going on in this output. So for our 2 processes, there's SQL Server and then my memtest program. We can see minor faults. Remember, that's the allocation. We can see major faults, which that's going to be going out the disk to read that memory back into space. And you can see there's 675 major faults at that time interval. Our virtual address space, so SQL Server had 18 gigs, we had 10 gigs, and the current memory allocation of real memory, 1.8 and 9.7. So the big consumers of real memory on our system. Now, back into that status file again, if we look here, we're going to see some more interesting information with the memory layout. So we can get information like, where is that swap? So how much of this process address space is currently on swap? And so here we see about 500 megs of SQL Server is actually swapped out to disk. Cool. Now, if we go and look at physical memory attributes of the system, let's kind of look at how SQL Server sees the underlying memory. Now, if I run select from DMOS sysmemory and run that, SQL Server, because of the configuration of SQLPAL, is only going to see about 9.4 gigs of that 12 gig, of the 12 gigs that are available in the physical system because of the abstraction that is SQLPAL. And that's a configurable attribute. And roughly, you're going to get an 80% allocation into the SQL Server process. And so that's another key element when it comes to the scalability of SQL Server on Linux systems, is knowing that SQL Server isn't going to see all of the base OS. So we had 12 inside of Linux from the real operating system and the real hardware, but SQL Server only sees 9.4 because of SQLPAL and how it exposes that memory into SQL Server on Linux. All right, so let's go ahead and close that and go ahead and jump down. We're going to look at one more query here, and we're going to look at our memory state. And so SQL Server on Linux will evacuate the caches. And so here we can see the in sysdm or sysdm OS sysmemory, the total amount, total physical available, and will respond to memory pressure events. And so here we can see that the current memory status is, it's a secret to everyone, physical memory usage is steady. So we've reached the point of stability inside the SQL Server process, even though we're applying this crazy amount of external memory pressure. Cool. So let's get and clean that up. Break out of memtest. And if I go and I kill memtest and I look at htop again, what we're going to see, since we're still running that read workload, now our swap's way reduced. We're doing a bunch of disk I/O because we're bringing all of that data back into memory. So we can see at the bottom here, the SQL Server process, which was shrunk down to about 1 gig, is now going to grow back up to 8 gigs or max server memory. And so we'll let that grow as it reads all of that information in for the next demo. So it's going to break out of there. Oop, got to break out of there. Kill off the workload because you can probably hear my CPU fans kicking on, and get that stopped. Cool. So let's jump back over to here, and we're going to look at disks and file systems. Now, disks, that's really the story behind looking at disks from a perf standpoint. It's very similar to what you're used to using on the Windows side of the house. And so we have things like sectors, which are the physical allocations, which are going to be of some size based on the actual physical disk that you're consuming. We have blocks, which are going to be the logical allocation unit and also the fundamental unit of I/O, right? So that's what the kernel is going to do when it needs to talk to the underlying disks. And of course, disks have finite performance characteristics in terms of bandwidth and latency, right? So how much data and how fast am I going to transact with that? And so all of this is very similar to on the Windows side of the house. It's just those analogs onto the Linux side of the house. So we have storage interconnects. They could be internal, they could be external, right? So we can have local disks, we could have remote disks connected via fiber channel, and those will have different performance characteristics. And so the key thing to know about this is baselining and making sure that you're getting the throughput and the latency that you're supposed to be getting from the hardware that you have allocated in your system. Now, from a file system standpoint, the Linux file systems you're going to see in mainline systems is going to be XFS, which is the default on Red Hat systems, and also ext4. So these are the two that are supported by SQL Server on Linux. You do have a configurable block size, but that's really not going to have that much of a performance impact on your workload. The default is going to be 4. Now, the key thing about block size when it comes to which one do you use, talk to your storage vendor is kind of my go-to advice on that one. There might be an optimal block size for your particular storage device. Now, when it comes to what do we want to look for, we need to find out when this happens. Like, when do we saturate the disks, or when are we at the point where we're dispatching I/O, we start to see queuing? All right, I'm going to look at some tooling to help expose that. We care about swapping, because in those scenarios where we are swapping, we're going to be driving a crazy amount of disk I/O, trying to keep all of the processes happy in their virtual memory allocations. And that's one of the reasons why systems like Kubernetes don't have swap files, because in Kubernetes, they'd rather just kill that process and let it restart somewhere else in a cluster than bring down the performance of a whole node because an individual process is swapping. Now, conventionally, we're going to have caching is really fantastic for disk subsystems, except for relational database systems, and that's going to be managed inside of the buffer pool. And as we alluded to a second ago, baseline. What are the actual performance characteristics of your disk subsystem, and what should they be, and are you hitting those? And so the tooling that we're going to use to answer those questions are going to be tools like IOStat and IOTop. PITStat's going to show up again, and of course, my favorite monitoring tool is DStat. And so let's go ahead, jump into a demo, and look at these tools and how they work. And so back to our CheckDB workload, kick that off. And we're going to look at IOTop as the first tool to tell us what's going on. So I'm running CheckDB in a hard loop, and at the top here we can see total disk read and total disk write. So heavy read workload because we're doing CheckDB, and so we're getting hundreds of megabytes of throughput per second. The difference between total and actual is this is going to be in kernel mode, and this is going to be the actual dispatch to the disk. And it's possible that we have cached data, so this value could be higher than the actual data. So in this list, though, we can sift out pretty fast that SQL Server is the driver of the majority of I/O on this system. Another tool to help us get a view of that is PITStat. And so here we can see PITStat, which is going to refresh every second. And we can see that we're driving a lots of I/O, kilobytes read, kilobits write, and which process. Again, another way to sift out who's consuming the most I/O. Let's go ahead and jump down and kill our workload, bring that into the foreground, and kill that off. Cool. All right, so let's jump back over to the presentation and look at some monitoring tools. So everything we've looked at so far is kind of pinpoint surgical. What's going on in CPU, what's going on in memory, what's going on disk, right? What if I want to get a bigger picture view of what's going on? And that's where tools like SAR and DStat come in. And so SAR, System Activity Reporter, is a tool that we can install that will periodically collect information and store that perf data over time. And so that's going to help us answer that question of what happened when. So I install SAR, it registers itself as a cron job, and it periodically samples data, so I can go back and look at what happened at 12 o'clock yesterday from a performance standpoint and pull that information out. I can also get it to generate an email reports to me periodically so that I can really get a feel for how this individual system is performing. Now, from a baselining standpoint, you can use DStat and write information out to CSV and generate some really good charts and graphs on which resources are being consumed. Remember, DStat exposes lots of information across CPU, disk, memory, and also network. Now, one thing that I do want to do is kind of correlate for you what is the system attribute that we're looking at, what's the perfmon counter that you're used to looking at, and what's the Linux tool and the values from that tool to kind of draw the connection between what you're used to seeing in perfmon and what's available to you inside of Linux. And so from a CPU standpoint, you're used to looking at percent processor time, right? Top, and that's going to give you CPU usage. Remember, I want to focus on load average. Now, memory, so percent memory bytes in use, right? On the Windows side of the house, free minus M. So we have total, used, free, and cache are the key values there. Disk space, so we have percent free. We didn't look at disk space in our demos, but we have df minus h, which is going to expose the actual per mount disk usage on our system. We also have IOs, right? That's a big one for DBAs, is how much IOs are we transacting under a workload. So we're used to looking at disk transfers per second. If we use IOstat with the minus dx parameter, we're going to have transactions per second, reads per second, and writes per second are the key attributes there. From a latency standpoint, we're used to seeing average disk seconds per transfer. Again, IOstat minus dx, you're going to look at awaits. Service time you'll see, but service time has been deprecated. It's still in the output, but don't consider that valid. So use awaits. If we want to find out if we're our average disk IO size, right? So IOstat minus dx, and look at average request size in that output, and we'll know how big our IOs are. So kind of those two values together between the number of IOs and the size of IOs. And also from an interface standpoint, bytes per second, which cracks me up because I don't know a network engineer on the planet that communicates values in bytes per second. So caution when you're looking at that, it's not bits per second. And the tooling that we can use for that, ifstat, BWMNG, and nload are going to be the values there, and those are going to be reported as bits per second. And also DStat. DStat will surface almost all of this data. From a tooling standpoint, for monitoring SQL Server, you literally have all of the same stuff that you're used to because SQL OS gives us DMVs and extended events, right? And you saw me use DMVs when I went and looked at the memory layout that SQL Server saw. And so we have all of that information available with us, and we can use extended events to extract the additional performance data that we're used to pulling out. Now, there are a new collection of tools that are available to us for running SQL Server on Linux. So PSS Diag has come out with PSS Diag for SQL Server on Linux. And so all of the tools inside of that PSS Diag app, or I guess suite of apps, are a lot of the tools that we looked at today. So things like PIDstat and IOstat and top and HTOP and pulling information on a procfs. That's all the same stuff that's inside of PSS Diag. So that's literally the same tools that Microsoft is using to extract perf data for SQL Server on Linux. Now, DBFS is a way that we can expose DMVs inside of the file system. So similar to /proc, where the kernel is going to be exposing information about what's running on the system, Microsoft has implemented as an open source project on GitHub the ability for us to expose DMVs inside of the file system. So we can have literally in /dbfs, you'll see all of the, if you configure this correctly, you'll have all of the DMVs available to you to query at the command line inside of Linux exposed as a file. Now, Grafana is a tool that's going to help you build their fantastic dashboards, like good visualizations of performance data over time. And check out that link there. And also, Tracy Baggiano has given a presentation on this exact topic using open source tooling to visualize data and specifically uses Grafana. So I strongly encourage you to check out that link there and her presentations on that same topic. And so we think we've covered a lot in a pretty good amount of time. I came in just under 1 o'clock, but we went through what Linux is, right? Like what the system architecture is and kernel mode and user mode and the importance of that. We looked at the architecture of SQL Server on Linux and how it's implemented in a way that it's Windows running on Linux inside of this thing called SQL and how it interacts with the base OS. And then we looked really closely at each of the core system components, CPU, memory, and disk, and their core OS abstractions, processes, pages, and file system. And we also looked at some tooling. So I have lots of resources available to you. So grab the decks or watch the videos when they're online. But if you have a question, hit me up via email or on Twitter. And I blog a lot about this. So memory pressure is a big topic that I like to blog about. Kubernetes is also a topic that you find me in containers blogging about a lot. So go ahead and check out that information there. And I have a bucket of Pluralsight courses around these same topics. If you've never used Linux before, I have a course for that. Deep dive perf data, go ahead and check out that advanced network course, and also a course on just administering and working with SQL Server on Linux. Shoot me an email and I can get you access to that content for free. I'll give you a free access code and you can get into those courses well, not say at my expense, but for free because I'll give you free trial codes. So if there are any questions, you want to go ahead and grab those now?
Okay. Just a few. I bet people aren't ready. They're still absorbing it, so they're trying to formulate their questions right now.
Cool. We can hang out for a little bit.
Okay. So, and this came in early, and I'm sure you answered it. There is a container version of SQL for Linux, but there's also the SQL for Windows-based container. Which one were you covering on this one?
So I'm speaking entirely from a Linux perspective and Linux containers. I actually have not worked with Windows containers for SQL Server. I've worked with production .NET applications that are running Windows containers, and they have their own, let's say, uniqueness when it comes to how they work. So.
Awesome. Okay. Also, somebody was curious if the tools can be useful in container environment.
Yes, hold that question. I want to pop one thing off the stack from the previous question. Windows containers are in preview, and I do believe you still have to sign up for that to get access to those. So if you do want to work with Windows-based containers for SQL Server, check with the product team for access to that. What was that next question? Data, perf data. So yes, when you're talking about how a container consumes the resources from an operating system, if you're running a Linux container on a Linux OS, which is what you're going to do in production, you're not going to run a Linux container in production on a Windows base OS. When you're a process up and running inside of a container, you think you're isolated. So if you're inside the container and you use all these tools, you're going to see just your view of the world. But if you have privileged access to the base OS, which as an administrator we likely would have, all of these tools would be able to see that process running, because a container, excuse me, is just a running process on an operating system. 1 second.
An hour talking is a long time.
Okay, I'm back. So yeah, just to reiterate, inside the container, yes, you could use these tools, but you're just going to see yourself. Outside the container, if you're logged into that base OS, all of these tools will expose that same exact perf data. In fact, you'll see SQL Server, the process, executing on that base OS with a regular numeric process ID that's not 1. Inside the container, it'll always be 1 for the parent process and likely 8 for the child process.
Okay, fantastic. And then we had a couple more come in. For production system, would you still recommend using Linux Pacemaker?
That's the answer to that.
Caution? Is that a caution flag?
Yeah, so the pacemaker thing, if you're skilled at pacemaker, then yes, that's what that comes down to for me. If you feel comfortable in using that to implement availability groups backed by pacemaker for the cluster resources, then yes, do that. If not, then no, don't do that, because one of the key elements that people forget when they're building high availability systems is the people component, right? Can you support that tech effectively? And when something goes wrong, can you react quickly and fix that issue? And so is that kind of put that back into the, can we support the system most effectively standpoint. So yeah, it's production ready, but can you support it in production is the big part that I kind of evangelize about that.
That's awesome. Okay. So everyone, I did put in the link to the YouTube channel for the group, so you can find this recorded session on probably tomorrow. I will send out an email also when it is finished uploading. And then, of course, Anthony, you have resources on your blog, which you'll be able to find that URL also via the website. Fantastic. Lots of good information. Had lots of people ask for the recording because they would probably want to go back and watch it several times. So much good information. Thank you so much
Thank you.
for joining us, Anthony. Really appreciate it. Appreciate you sharing your vast knowledge and in-depth knowledge. And for all our Australia cohorts that are sleeping right now, but we'll probably watch this later, you guys are definitely in our thoughts, and we hope you're staying safe out there. Okay, have a good one all. We'll see you in February for performance tuning with machine learning. Okay, have a good day. Bye all.
Awesome, thank you.
Thanks, Anthony.